Okay, welcome everyone to the Zoom Algebraic Geometry Seminar. We're very pleased to have Fatemeh Rezaee from University of Edinburgh, and her topic is wall crossing pathologies in dimension 3.
Thank you very much for the invitation. It's a pleasure to speak here in this seminar. Let's look at the plan of the talk. First, I started stating the first goal, and then I mentioned some previous work on this. And later I need some definitions to state the second goal, and then I mention some previous work on that as well. And then I give an introduction, a very brief introduction to Bayesian stability conditions, and then be back to the problem and start doing the wall crossing, and then state the theorems that we need and the idea of the proofs. And in the end, we will see some more pictures. Okay, so the first goal is to describe the moduli spaces associated with canonical genus 4 curves, the following moduli spaces, which are moduli space of PT, stable pairs, and also the Hilbert scheme. So the way that we want to do this is via an effective control over its wall crossing to determine the components of the Hilbert scheme, basically. And so as an intermediate step, our strategy basically uses this space of PT stable pairs as an intermediate step, what we are describing Hilbert schemes. Okay, and this is basically maybe the first example. That's the components of moduli space with several irreducible components completely determined by wall crossing. Okay, so some previous work on description of moduli spaces in higher dimensions are as follows via wall crossing. Okay. So for the case of Hilbert schemes, we have these two examples of Hilbert scheme of twisted cubics, also Hilbert scheme of elliptic quartics. Twisted cubics, the wall crossing is due to Benjamin Schmidt and Antubingu Shaw. But also there are classical results on this, which was given, for example, by Piene and Schlesinger, and also by Linksrud, Piene, and Strume. And okay, and then for the Hilbert scheme of elliptic quartics, then the wall crossing was given by Gallardo Huerta and Benjamin Schmidt. Also, there are some classical or maybe some non-wall crossing results on these elliptic quartics, which are given by Ritzer and Weinsencher, and also by Gottsman, and more recently by Dovichin and Nollet. So this was for the Hilbert scheme, but also for higher ranked or moduli space of objects of higher ranks. There are these examples of moduli space with Chern character 2, 0, minus 1, 0 in P3. This is due to Jardim and Anthony Mashosha. And also for rank 2 ships with maximal third Chern character in P3 is due to Benjamin Schmidt. And I don't know any example of moduli space of the stable pairs to list here. So, okay. Then we have some definitions that I need for stating the second goal. I will define these things more precisely later, but just for now, let's look at this. Let X be a smooth projective variety and be a class, for example, like a Chern character. Then for an object in the derived category of coherent shapes on X, we say that this object is stable with respect to some slope. I will define this later more precisely. If for each sub-object of this object, the slope of this object is greater than the slope of all its sub-objects, and we say semi-stable if you have this inequality here. And so also we denote by a stab of X to be the space of all stability conditions if you assume that exists And Tom Bridgman showed that this is a complex manifold, and sometimes we call this a stability space. We are talking about Bridgman stable objects here. And we denote by m sigma of V to be the space of all sigma stable objects of class V in the derived category. Also, let me remind you the definition of stable pairs. So for a non-singular tripod X, we define Ponti-Thomas stable pair F and S to be like this. F is a pure sheaf supported on curves in C, and S is its section such that the kernel is zero dimensional. And this is the stability condition for these stable pairs here. Also, let me remind you the definition of a Grothendieck group. For a category C, you can find a Grothendieck group K0 of C to be a free abelian group, which is generated by objects in C, and we have this relation when we have such exact sequence here. And we notice that this Grothendieck group is usually not finitely generated, so I will get them back to this point when I talk about Bridgman stability later. Okay. Then we have one more definition, which is this minimal model program. Let M be a smooth projective variety. A minimal model program is a sequence of either divisorial or contraction or Philippine contractions, such that we have this M is equal to M0 and M1 up to Mn, such that each Mi is at least or at most Q factorial, given that the worst singularity that we can have is Q factorial. And Q factorial means that any Venn divisor is Q Cartier. And this last space here is either a minimal model, which means that the K of that is Neff, or it has a fiber structure in the sense of Mori. And so we refer to these steps as MMP steps or MMP operations. Okay. Okay, and then okay, let's assume that this stability manifold exists for our space X, and in ideal situation, this stability manifold is decomposed into this wall and chamber structure. What is wall and chamber? Well, wall is a locally finite codimension one submanifold of this stability manifold, and the complement of the walls are chambers. And we have this property for each chamber that for any stability conditions, inside the chamber, it doesn't matter which stability condition you choose, the modular space of stable objects with respect to that stability is always constant, inside this chamber. So basically, we only associate one modular space to each chamber here. Okay. Okay. And when you cross a wall, then this modular space changes, and you can imagine that some objects in this space, in this modular space, will get destabilized, and we call that the set of that object the destabilizing locus. And okay, and I interchangeably say that, for example, instead of saying the chamber C, I'd say the chamber, the MC of the or M. Okay. Okay, the next picture is related to explaining this correspondence, wall crossing and MLP correspondence. Let X be a variety and M is the modular space of stable objects. So this is M sigma of V, I assume, associated to the chamber in a stab of X. Basically, I'm saying, okay, this is a stability manifold, and one of the chambers, the modular space associated to the chamber is this M. So we know that in ideal situation, we have wall and chamber decomposition here. And on the other hand, you can run the minimal model program for this M, and all these MMP steps and MMP operations happen, in the movable cone of this M here. Okay, and also you have wall and chamber decomposition for the movable cone by rational geometry. in this stability space, you change the stability condition, and in here you change the movable divisors, and you go through this wall and chamber decomposition here. And now the question is that how can you relate these two decomposition for this chamber M here? And well, or in other words, we are asking, is there a correspondence between the Bridgeland wall crossing in the stability space on X and the Mori wall crossing in the movable cone of M? Okay, basically, this is our second goal to answer this question. Okay, first, let's look at some previous works. For the case of surfaces, the answer to this question is positive. For example, for the case of K3 surfaces, the result is due to Boyer and Macri. I will give more details on this shortly. For the case when X is equal to P2, for example, for Hilbert scheme of points in P2, the result is due to Arcara, Bertram, Kuzmin-Heisenka, and also Bertram, Martinez-Bang, and also Chunili and Shaoli Zhao. And when X is Enrico surface, the result due to Neuer and Yoshioka, and also Thurston Beckman. And when M is a smooth projective surface, the result is due to Toda. Let's look at the case of K3 surfaces more carefully. We just want to explain this correspondence for the case of a K3 surface. Let S be a K3 surface and V a primitive glass. The next theorem just implies one direction. Let's get back to the picture. In this picture, we have two directions, one from the right to the left, one from the left to the right. It means that we want to see each wall crossing here as an MMP operation here, and each chamber here or each moduli space here as a moduli space of a Bridgeland stable objects here. So the first theorem just says that we have this correspondence from the left to the right for the case of surfaces, which is this theorem. We said that for any two stability condition, generic stability condition, generic means that the stability condition is not on the wall, then these two moduli spaces, these two associated moduli spaces of Bridgeland stable objects are birational to each other. We knew that, within a chamber, they are actually identical, but this theorem says that even if you are not in the same line, they are still birational to each other. And so this implies this, wall crossing implies MMP operation. And using this theorem, we can identify the Néron-Severi group of these two moduli spaces. And then if C is a chamber, then the result defines a map from this chamber to the Néron-Severi group of the associated moduli space. And the image of this is in the ample cone of the moduli space. Okay, then the next theorem, first of all, implies the other direction from the right to the left by gluing those map ICs together. So you fix a stability condition here, and then under the identification of these Néron-Severi groups, these maps ICs could glue together to get this map L from the whole stability space to the Néron-Severi group of this of the moduli space of sigma stable objects. And then the second part says that this map is compatible in the sense that for any generic stability condition, sigma prime, the moduli space and sigma prime is a birational model corresponding to the image of the stability condition under this map. And in particular, every smooth K-trivial birational model of this M sigma of B appears as a moduli space of Bridgeland stable objects for some chamber in the stability space. This is exactly the meaning of this here. Okay, of this implication. Or in other words, we are saying that any birational model can be reached after wall crossing as a moduli space of stable objects. Okay. Okay, then that was for the case of surfaces, but for the case of triple, in this talk, we only look at the case of P3. We give an example that none of these directions hold. Okay. So first, let's have a background on Bridge-line stability conditions in case you are not familiar with this. So first, very roughly, we have this picture, and then I make things more precise. So the idea is that you start with an object in the derived category, and you want to associate a complex number to it. So basically, this object in the derived category, you take it in heart of a bonded Ttest structure, which I will define later. And this is supposed to be an abelian category, or more precisely, you take your object in the K0 of this abelian category A. But as we said, I mean, this K0 of A is usually not finitely generated, so it's easier to work with a finitely generated group. So we fix a finite rank lattice, and we associate a vector to this space to be in that finite rank lattice. So this finite rank lattice is an finitely generated abelian group. And basically, in this talk, I mean, this vector is just a Chern character. And then the next step is to just associate a complex number to this vector. I mean, denoted by Z of B of B, and we call it the central charge. Okay, and we want to have this condition that this complex number should be in the upper half plane union this negative real line. And then having this complex number, we can define the slope of E to be the minus real part of this complex number over the imaginary part of this complex number. Okay, so then having this condition here, we can compare the slope of this to a slope of its sub-object and define the notion of stability or semi-stability. Okay, now let's make the definition more precise. First, we start by a stability condition on abelian categories. Let A be an abelian category. A pair A and Z, I mean, is a stability condition if Z is a group homomorphism, which, as I said, we call it central charge from the grothendieck group to C, such that we have these two properties. The first property is just the one in the picture, that for any non-zero object, imaginary part is greater than or equal to 0. And if it's 0, then the real part must be negative. And also we want to have some Harden or Riemann filtration that says that for any non-zero object, we want to have this filtration by these EIs, such that the factors are semi-stable objects and the slope of those are decreasing. And basically the motivating example with this definition is the case of curves. When you have a projective curve, you can define Z to be minus degree plus I rank for any object in the coherent, in the category of coherent shape. And you know that for each object in the category of coherent shape, we have two numerical invariants, rank and degree. And so both of them, are here and are included, in this definition. So you can check that, I mean, that this abelian category of coherent shapes and this C that we define gives you a stability condition in this sense. Okay, but then this was the case of curves, but when you increase the dimension, then it happens that, if you take this category, this abelian category of coherent shapes, and if the dimension of X is greater than 2, then you cannot find any central charge with those properties. So the solution to this issue is that you find another abelian category in the derived category instead of this category. And because an abelian category is defined by its torsion pair, we want to use this notion of torsion pair. Let me remind you what was the torsion pair. A torsion pair in an abelian category is a pair T, and F of full additive subcategories such that we have these two properties. First of all, there is no harm from T to F. And second of all, for each object, there exists this short exact sequence, and each object E fits into such short exact sequence from T to E to F, for T in T and F in F. And so using this, we want to define our abelian category, which we call it hearts of a bonded Ttest structure, a prime on dB of X to be a full additive subcategory with these two properties similar to these two properties here. First of all, there is no harm from A shifted by I to B shifted by J for any I greater than J, and also we want to have some Harder-Narasimhan properties. I can check that this is, with this definition, this is actually an abelian category, and you have this property that the K group, K naught of A prime is the same as K naught of X, the same as K naught of the derived category. Okay, and as we saw in the picture, we fix a finite rank lattice and a group homomorphism from the Grothendieck group to that finite rank lattice, such that the central charge that was defined from the Grothendieck group to C is factorized via this. So we can, for defining the central charge, we can directly start from this finite rank lattice instead of the Grothendieck group. Okay, so having this definition, we can now define the Bridgeland stability condition for any variety of any dimension n. This pair, which we denoted by sigma, A prime and Z, is a Bridgeland stability condition on the derived category if this A prime is the heart of a bonded Ttest structure and Z is a central charge, which I defined it from this finite rank lattice this time. And again, we want to have this property in the picture in the upper half plane union. The image is supposed to be in the upper half plane union negative real line. And in addition, we need to have some support property. I'm not going to describe this support property because it's a bit technical, but for us, this support property just guarantees that this stab of X, this space of all Bridgeland stability conditions, admit a wall and chamber decomposition. Or more formally, we just saw it in the picture, but more formally it means that, okay, for each chamber, this modular space M sigma of B is independent of the choice of the stability condition in the chamber. Also, walls consist of strictly semi-stable objects of this class B. Okay. Then let's see how can we basically construct this heart of a bonded Ttest structure for the case of threefolds that we care about. Stability conditions for threefolds is due to Bayer, Macri, and Toda, and tilt stability is an intermediate step between a slope stability and Bridgeland stability for the case of threefolds. So how can you define heart of a bonded Ttest structure? First, if you think of the derived category as this strip, and you think of this abelian category of coherent shifts inside it as this block here, which consists of this T and F, then you have all the shifts of T and F here, or all the shifts of this A here, which covers this derived category. Then to find another abelian category, you take these T parts of this, and instead of F, you look at this F shifted by one part, and you take this block here. And we call this process tilting. And this gives you a new abelian category inside the derived category. If you are in the case of surfaces, then at this step, you have a heart of a bonded Ttest structure. But if you work with triples, then you need to tilt it once again. And you do, just the same thing with this, starting with this block here to get this here. And this will be the heart of a bonded Ttest structure for triples. And you can imagine that you can tilt and tilt and tilt, and for any dimension, you can define the heart of a bonded Ttest structure. But the problem with defining Bridgeland stability condition is defining a suitable central charge and proving support properties. But for the case of tripods, or at least for the case of P3, we know that this does exist. Basically, for tripods, this is a conjecture by Bayer, Macri, and Toda, and it's proved for many cases of tripods. In particular, for P3, we have the result, which is proved by Macri, and also by Macri Stellari, and also by Chunili. So they define central third and they prove some support property. And so all these guarantees that there exists a wall and chamber structure on a stab of P3. Okay, this is all on the background and the stability conditions. And now let's get back to the problem that we had. Here is the setup. Let me remind you that if you have a smooth non-hyperelliptic genus 4 curve, this can be embedded into P3 as a 2 and 3 complete intersection curve. Okay, and then a question one may ask is that how can you compactify this space of all such curves? And because these curves are embedded in P3, one could think of heat beta scheme of such curves. But the problem here is that this heat beta scheme of this case is very complicated, and so instead of that, we look at Rezaee stability condition and the derived category. So depending on the choice of the stability condition in the stab of P3, this gives you these moduli spaces M sigma of this 1, 0, minus 6, 15. This is just the chain character of ideal sheaf of such curves. Okay, so we have this moduli space, and we want to see how this changes. Basically, we take a path in the stability space to understand how this moduli space changes. I will show you a lot of pictures on that later. So in the beginning of the path, we just get that compactification just for free. Okay, this compactification would be a P15 bundle over a P9. This P15 is for the choice of cubics, and P9 is for the choice of quadric surfaces. This parameterizes some non-torsion free sheaves in addition to the ideal sheaves that we were interested in. Okay, this is just the beginning of the path, but if you keep crossing the walls, then the second wall gives you that counterexample that I promised, that fails the wall crossing and MMP correspondence for the case of P3. And if you go all the way to the large volume limit, then you can also recover the Hilbert scheme of such curves. And as an intermediate step, you can also recover the moduli space upon the Thomas stable pairs as well. Okay, let's do this. To do this, we first start with a Ttest stability, as I mentioned, which was an intermediate step between a slope and Brisbane stability, and then translate things to Brisbane stability. Okay, let's look at some pictures to see what we are doing. So this stab tilt P3, this is the space of tilt stable objects on the derived category. If you look at the walls here, in our case, we have these 4 walls, these 4 nested semicircles. And in general, walls in the tilt stability space are either nested semicircles or vertical lines. Okay, but in our case, we only have these 4 semicircles, so the vertical line is not the case in our case. Then if you translate this picture to the Brisbane stability space, to the stab of P3, then some of these walls might get decomposed to some more walls. And you don't have semicircle anymore, but you have some more complicated equations. So let's go to the Brisbane stability space. Then this picture becomes this. Okay, basically you see that these first 2 walls remain just single walls, but the third wall becomes, like 3 walls. And the last wall becomes 7 walls here in this stab of P3. And we have a special curve here, or a special wall here, that separates in the large volume limit, it separates this Hilbert scheme and the space of Ttest stable pairs. And you see that these 7 walls here becomes only 1 wall on this side, on the right side of this curve. So it's better to just cross all these walls here to first describe the space of Ttest stable pairs, and then cross this wall between them to describe the Hilbert scheme instead of, going this way. So basically, we start from the empty set where this is somewhere when there is no stable object. And starting from here, we take, a path very close to this special curve here and go all the way here to the large volume limit. Okay, let's do this. First of all, the next theorem just, describes this wall here. This is the wall which is interesting, which basically fails that correspondence. But in order to, I describe this wall, I need to also say something about these 2 walls as well. So the statement of the theorem is just about this wall, basically. Let's first look at this. So we fix this chain character and say that, okay, there is a wall crossing from m sigma minus to m sigma plus. This sigma minus and sigma plus are 2 stability conditions in adjacent chambers in the stability space. And we claim that, okay, this the first moduli space associated to m sigma minus is something nice, is smooth and irreducible. But this one, m sigma plus, is not irreducible. It has a copy of this previous one and a new component, a new irreducible component. Okay. And then the next part says that first let a sigma naught be a stability condition on the wall between these 2 basically moduli spaces, or the chambers of these 2 stability conditions, sigma minus and sigma plus. And then I claim that there exists a small contraction from this m sigma minus, from this nice space, to m sigma naught. And so because you have a small contraction here, you expect to have another small contraction on the other side to complete this as a flip. But this doesn't happen because on the other side, we get a divisorial contraction. And also we can show that we can show that both of these contractions have a relative Picard rank 1. And so in particular, that implies that this space here is not Q factorial. And because it's not Q factorial, this cannot be appeared as a MMP for this M sigma minus, because they were all supposed to be Q factorial. Okay, so let's see how we can prove this theorem. First of all, let me be more precise about those spaces that I introduced. This M sigma minus is a blow up of a P15 bundle over P0. But I already said that this was that compactification that we were looking for. So, in this picture, that compactification, this P15 bundle over P9 happens, here, just right after this first wall here. And then this wall, this second wall, gives you, this is just a blow up of that compactification. And the result is just this M sigma minus here. And then, the next wall, which we are describing, we have this M sigma minus here, And then when you cross this wall, you get this new component M prime, apart from this birational copy of this here. Okay, so and this new component in this chamber here is a P17 bundle over this cross-Monnian cross FL2, where FL2 is the space that parameterizes flags Z2 inside P3. The P is a plane and Z2 is a zero-dimensional length 2 subscheme of this plane. Okay, so we have this, and to prove the theorem, for example, we need to say that first of all, this map from this M sigma minus to this is a small contraction, and the other map from this M sigma minus twiddle to this is a divisorial contraction. So this is not a Philippe. This wall crossing is not a Philippe. Okay. So to show that this is a small contraction, we need to look at the destabilizing locus inside this when you cross the wall. And also to show that this is divisorial, you need to more carefully look at the intersection of these two components here. Okay, so let's see how this works. Okay, as I said, to say that the map phi is small, we need to describe the destabilizing locus. Basically, we don't need the detail of this proposition here. It's just that just looking at the dimension of this locus here and then noticing that this is a P1 bundle, then that just simply implies that this is a small contraction. And more difficult problem is that is to show that the other map is divisorial, which we need to look at the intersection of those two components. Basically, this theorem describes the intersection, which I will skip the details and also the proof because we don't have much time left. But the corollary of this theorem, of this description of this intersection would be this. Let me go to the corollary. Okay, the corollary is this, that the singular locus of this M sigma minus, M sigma plus is exactly the intersection of those two components, which is exactly the exceptional locus of this map that we wanted, or exceptional, and basically we say we can see that this is exceptional divisor. And so all this shows that this map was a divisorial contraction. So we get one small contraction from M sigma minus to M sigma naught, which was this, and a divisorial contraction from this M sigma minus twiddle to M sigma naught. Okay, so then okay, it's also not very difficult to show that the Picard rank of both of those are 1. I just skip this slide. But how can you show that you're having all this? How can you show that this M sigma minus twiddle is not Q factorial? Yeah. First of all, let's assume that it is Q factorial. Then we already proved that this map psi is divisorial and also is of Picard rank 1, and that M sigma naught is the image of this this M sigma minus twiddle, which we assume that it was Q factorial under this map psi with these two properties. Okay, and that implies that this M sigma naught, this image must be Q factorial as well. This is, I mean, just can be implied by the result of Kolar and Mori. And on the other hand, this M sigma naught is the image of a Q factorial variety. You know, this M sigma minus was even smooth, so in particular it's Q factorial. But this is the image of this under a small contraction. So this means that this cannot be Q factorial. Now combining 1 and 2 gives you a contradiction. Therefore, this space cannot be Q factorial. Okay. So, no, okay. We said that this is not a flip. I mean, we have divisorial and a small, but how can you relate these two basically via maybe another auxiliary space? First, let's look at this exceptional divisor here in this M sigma minus theta. This is divisorial contraction, and then take the image under this map, the side of E here. And then look at the pullback of this here in M sigma minus of V. This is another locus here. And now you can blow this up along this locus here to get this map, to get this space N double prime. Okay. And then the universal property of blow-ups tell you that there should be a map from N double prime to M sigma not M sigma minus theta, because basically, you know, we have this map from this M by this construction. We have a map from N double prime to this M sigma naught, such that, you know, the pullback of this psi of E here is Cartier. You can check this. And so in the category of all varieties over this, with this property that the inverse image of this is, or the pullback of this is Cartier, this the blow up of that is just the final object. So that's why we have this map from N double prime to this map here. So that's how you can relate, you know, these two spaces, which are supposed to be birational, to each other via this third space that we just constructed. Okay, okay, but okay, the flip is not here, but the flip of this with respect to this small contraction must exist. Let's see how we can have the flip somewhere here in this picture. Okay, this slide, I mean, this back square here is just the previous slide that I just described. And here I just added this node here, this N. This N is just supposed to be the flip of this M sigma minus. Okay, and then we play the same game this time with this N. Again, we start with this exceptional divisor here, and we look at the image of this here, and then we again look at the inverse image under this small map this time to get this locus inside this the flip. And then again, you can blow this up along this locus to get N prime this time. And again, the universal property of blow ups tells you that there must be a map from this N prime to this M sigma minus theta, because again, you have this map from N prime to M sigma not with the same property that the pullback of this psi of E is Q Cartier here. Okay, so that's how you can relate these basically three spaces: one M sigma minus, M sigma minus prime, and also this flip here via these two auxiliary spaces N prime and N double prime that we just explicitly constructed. Okay. And then let's look at the movable cone of either of these two spaces, N prime or N double prime. If you look at this, you see that these spaces that we cared about just live on the sides of this or on the walls of this movable cone here. These are chambers. And in order to go from M sigma minus to M sigma minus theta, you need to walk along this broken line. First, you go to this M sigma naught, the wall, and then you go from the wall to this space here. And here we have this flip of that here. This is the divisorial direction, and this is a flipping direction. And now we can look at more the big picture that we had in the beginning. So basically, we cross this wall in the stability aspect. This is m sigma minus, this is m sigma minus theta. But on the other side, you are not crossing any wall. You are just walking along this broken line here. Okay, and so basically, this says that the wall crossing does not induce any operation here, so you don't have this direction. And on the other hand, for example, you have this flip here that cannot appear here as a modular space of stable objects, of regional stable objects. So you don't have this direction either. Okay. This is all about this the failure of the correspondence. Now let's go to the description of those two modular spaces, or basically let's cross the other walls. First, we have some notations. I think I already introduced this. O2 is parameterizes quadric surfaces in P3. U is the universal line over Grossmanian, and FLJ parameterizes flags ZJ inside P3, where P is a plane and ZJ is a zero-dimensional length J subscheme of the plane. Okay, and then this theorem describes the space of PT stable pairs. Basically, we cross the rest of the walls. First, we start. From the beginning. The first component you get is this main component, or the compactification of two and three complete intersection curves, which is this P15 bundle as we described. And then, as I said, the second wall, this wall here is just a blue up and it doesn't give you any new component. So we skip this. And then the next wall that produces a component is just the wall that we described, which produces M prime. So the next slide will be the description of M prime. As we said, this is a P17 bundle, but generically this parameterizes line union this plane quintic together with two marked points on that quintic. This is just the M prime. Okay, which appears here. And then the next wall, this wall here produces two irreducible components. The first component is this, is a P18 bundle over a U cross FL1, which generically parameterizes this picture here. Again, a plane quintic with a marked point, a line intersecting it, and a marked point on the line. And then the next component, which is given again by the same wall, is very similar to this, except that this time, this line and quintic doesn't intersect and you have one marked point less. Okay, and the next wall gives you three new irreducible components. And the first component is a P19 bundle over this, which generically parameterizes this. Again, you have a quintic line and two marked points on the line. The next component is very similar, except that we have this joint union and 1 point less. And the third component after this wall is a bit different. Is a C4, is a degree 4 curve in the plane, and a double line generically parameterizes this. And this is a P21 bundle over FL2. Okay, and then we have one last one to the PT stable pair, which gives you one new component, which is this a P21 bundle over FL6, which generically parameterizes this a degree 6 curve, plane curve together with 6 points at 6 marked points. Okay, I know that was the last and eighth component of this space of stable pairs. Okay. And then we have this overall picture here, all the components. This is the main component, and the rest appeared after all these walls here. Okay. Then The proof basically, for each wall is given by this pair A and B. These are basically the Jordan-Holder factors of the objects on the wall. So each object, its newly stable objects are given by such exact triangle from A to E to B. And for each A and B, this gives this locus projectivization of x1 of B and A inside the moduli space which appears after crossing the wall. And basically, we want to stratify the space of all these pairs A and B by the dimension of this locus here. And then for each stratum, we describe a general element and decide whether it is in the closure of the other strata or it has its own component. For example, if you get some maximal dimension, then that's obviously an independent component. And also, we have a lemma to show that when a component appears after a wall, then it will be survived all the way to the large volume limit. If you have this property, if H naught of a general object in an irreducible component which is created by a wall is an ideal shift, then that component will be survived all the way to the large volume limit. Okay, then here I have one explicit example. For example, we have one wall which is given by these two objects. This is A and this is B. This is a two-term complex. This is just OP minus 5. And this object E here, this two-term complex is, this wall destabilizes this because of this diagram here. Okay, then let's describe the Hilbert scheme now. Basically, we said that, okay, we needed to cross, one more wall. We already described this PT stable pair space, and we need to cross this wall to describe the Hilbert scheme. Okay. The next theorem describes this Hilbert scheme. First of all, the Hilbert polynomial here is 6t minus 3, because the degree is 6 and the genus is 4. And so this has this component. The first two components are the same. We already met these two components in the space of stable pairs, right? One is the main component and one is this component which didn't have any point involved. And the new component is this. This component generically parameterizes again a plane quintic, a line, and one floating point this time. And then the next again is similar, except that these two line and this intersect, and you have two floating points. And the last one is this degree 6 here and 6 floating points. Okay, and this completes this theorem and this description, the Hilbert scheme. So here we have the overall picture, all these components that I described. And okay, to prove this, I call this wall between this Hilbert scheme and the stable pair space the DTPT wall. Okay. And basically, this DTPT correspondence, we can see it as a wall crossing. This is due to Pondreponder and Thomas, and also Bayer and Toda, also other version by Marcus Jardim and Antonio Messocho. So this is the description, the explicit description of the DTPT wall given by these walls, ICIs and TI shifted by -1 for I1, 2, and 6. These CIs are Cohen-Macaulay curves of degree 6 and genus 4 plus I, and TIs are torsion shifts of length I. And basically, we have this fact that DTPT wall destabilizes all the components in the stable pair side that parameterizes non-Cohen-Macaulay curves. Because for those objects, the H naught is non-zero, so it would get destabilized like this, and we already described the wall. So, and this wall between these two large volume limits, it doesn't destabilize the two components that don't involve, the points that are just Cohen-Macaulay components, which is the main component and the component we just saw, because of this. And then it also creates these three new components. And the underlying Cohen-Macaulay curves are the same as in the PT side, except that you let the points float instead of being marked. Okay. This picture or wall crossing picture also matches some classical results. For example, there is this theorem by Hartshorne that gives you a bound on the genus of non-plane Cohen-Macaulay curves of degree D in P3. You have this upper bound, and if you check this for our case, and using also the degree genus formula, you see that, the only possible genus could be 5, 6, or for the plane curve, 10. And this implies that the length of the zero-dimensional subschemes that were involved were either 1, 2, or 6. These are basically the maximum genus minus this genus here. The maximum genus is 10 minus this. Minus the genus that we had, the genus 4. Basically, we already have this result by purely using the wall crossing without using, this result. Okay. For example, we don't have any curve with genus, for example, 7, 8, or 9. Okay, and another good thing about the wall crossing is that, you can imagine for any given Hilbert polynomial, there are a lot of configuration of reducible curves plus some points that could have that Hilbert polynomial. But the question is that which of these configurations exactly have their own independent component in the Hilbert scheme. For example, you can imagine that this example, you have a plane degree 4 curve and a degree 2 curve that intersected in 2 points. This obviously has degree 6, and you can compute that the genus is 4. So that has the Hilbert polynomial like 60 minus 3, but it doesn't have its own component in the Hilbert scheme. And why is that? Because this appears as the exceptional divisor of this wall crossing here. So this basically lives in the closure of this main component instead, because main component was here. Okay. And this, final remark just is the things that I just said. It just summarizes the things. Wall crossing can recover this classical prediction about the moduli spaces. Also tells you which generic configuration can have their own component. But on the other hand, it could be birationally unpredictable. And also it doesn't exactly, detect all the complicated properties and aspects of the modular space that we expect. Okay, so finally we have this picture here to summarize the components that we just described. On the PT side, we have this, and on the Hilbert scheme side, we have this. Basically, these Cohen-Macaulay components are the same, and the non-Cohen-Macaulay components, for example, we have 3 of them with the same underlying curves here with 2 points involved. You just let these 2 points to float to get this component here, and the same for the other components. And okay, this is, I think, this is all I wanted to say today. And thank you very much for your attention.
Let's thank Fatemeh.